In a solar system far away, a rocky world orbits a yellow sun. The pale blue planet could be mistaken for a long-lost sibling of Earth by interstellar observers. On a closer look, Dove is a colder cousin to Earth. Island arcs ring a vast, globe-spanning ocean that surrounds a newly formed supercontinent. Kilometer-deep sheets of ice bury volcanoes under the northern polar circle. Fields of glaciers stretch along the backs of rising mountains across the equator. Between the glacial heights and ocean depths, life continues to survive. Hello and welcome to Lands Unknown. During this world-building series, we will explore the planet of Dove and chart the development of the peoples who call this planet home. Supplementary videos will dig deeper into the process of world-building itself, as well as the decisions and research that shaped Dove. As an introduction to the world, this first video will build a foundation by looking at the physical geography of Dove from the deep past to the present era. If you enjoy this project, I would appreciate a like, comment, and subscribe if you haven't already. And if you really like it, then you can support me on Ko-fi. Here, we can see a Robinson projection of Dove in the present era. Before delving into the past, we should review a few notable characteristics that inform the project. First, Dove is an Earth-equivalent planet with an Earth-like orbit around a Sol-like yellow main sequence star. Dove is the same size and density of Earth, and has a similar chemical composition. A notable difference is that Dove has two small moons. The interior moon is a captured asteroid, while the exterior moon is a captured dwarf planet, about the same size as Ceres or Pluto's moon Charon. Both are visible from Dove's surface. However, they have a minimal effect on the tides when compared to the impact of Earth's moon Luna. The average global temperature at the beginning of Dove's present era is 9 degrees Celsius, which is equivalent to Earth's temperature during the last glacial maximum. These colder temperatures have led to extensive glaciation. The main ice sheet is advancing in the subtropics, alpine ice fields are growing at the equator, and year-round sea ice reaches 60 degrees latitude. Whereas on Earth the complexity of human society as we know it developed during a period of general warming, Dovian societies are contending with a cooling climate. The major land masses on Earth during the Cenozoic are separated by oceans and straits, but the present era on Dove is defined by the recent formation of the supercontinent Bacera in the northern hemisphere. The ongoing orogenies and biotic exchange between isolated ecosystems play an important role in the project. During the creation of Paleobacera, a large plate of ocean crust was trapped between colliding continental landmasses, creating the Tyche Sea. Instead of shutting down, the subduction zone on the eastern shore of the Tyche tore off several terrains from the north shore. The present islands are the most recent and significant superterranes. In addition, the Tyche Sea plays a pivotal role in the current climate regime, providing moisture to the interior of Bacera and snow in the accumulation zone of the ice sheets, even in the summer. Now that we have an idea of the present era, we can explore Dovian Paleogeography. "500 million years ago, the landmasses of Dove were part of the paleo supercontinent called Erukia around the South Pole. Over half of Erukia's land was below 60 degrees latitude in the southern hemisphere and covered in ice sheets. Mountain building during the formation of Erukia cast rain shadows over the interior and created deserts throughout much of the subtropics. Despite these hurdles, the first land-dwelling flora and fauna came to shore on the eve of the supercontinent's breakup. 450 million years ago, Erukia rifted into two continents, Paleolanea and Torcasia. By 400 million years ago, violent periods of extended volcanism spewed CO2 into the atmosphere as the major landmasses drifted out of the southern polar circle. Though the initial rifting of Erukia and accompanying large igneous provinces caused a mass extinction on land and sea, the following period enjoyed a warming climate that saw an explosive biodiversification event. 250 million years ago, a majority of Dove's land area is between 66 degrees latitude north and south. Zaalea rifted from Erukia in the breakup of Torcasia and collided with Paleolanea to form the recognizable shape of Paleobacera and the oldest phase of the Tyche Sea, after which Palomia broke away and drifted north. Since 350 million years ago, Dove has enjoyed a lengthy greenhouse period that will last another 150 million years. The abundance of vegetation caused the emergence of the first terrestrial megafauna. While much of Dove's continents were humid and sea levels were at their highest, the heat made Inner Lanea into a great desert. 150 million years ago, slightly cooler temperatures decreased aridity across the planet, leading to another evolutionary radiation, as plants and animals exploited new niches and adapted to the changing climate regime. The clades that make up the most successful life on Dove in the present era are first seen in this period. Around 200 million years ago, Erukia rifted into Zaalea and Erukia, opening up the Astarte Ocean and beginning their inevitable collision with Paleobacera. Erukia was the last vestige of Uya within the South Polar Circle, but the continent will drift far enough north that a southern circumpolar current will form. 50 million years ago, the continental plates are nearing their positions in the present era. Polomia has already made contact with northern Zaalea, and in the south, an ocean plate subducting beneath the southeastern coast of Paleobacera pulls Erukia in at an ever-increasing pace until the collision 25 million years ago. Polomia rapidly glaciated after a majority of the continent entered the northern polar circle about 100 million years ago, causing the average global temperature to decrease. Shortly thereafter, the completion of the circumpolar current around the South Pole accelerated the cooling of the planet. Between 100 and 75 million years ago, there was a prolonged period of severe biodiversity loss, killing 75% of all terrestrial and marine species, which set the stage for the speciation of the present era. In the last section, we follow the breakup of the supercontinent Uya around 500 million years ago, through to the formation of the supercontinent Bacera, which defines the present geological era. Bacera is composed of 5 major subcontinents. Working clockwise from the east, they are Zaalea, Launea, Polomia, Zaalea, and Erukia. Enclosed by Bacera are the Tyche and Agathie seas. Surrounding Bacera is the Aphrodite superocean, and in the southern hemisphere, the Astarte Ocean, which is separated from the Agathie and Aphrodite by island arcs, Erukia, and the southern ice pack. Here we can see the 4 most important active orogenies on Bacera. In the west is the Urzite orogeny that was caused by the collision of Zaalea and Launea. The Urzetekis are the easternmost range of the Alaean cordillera, which began with the breakup of Uya and passed through alternating periods of subduction and accretion over the past 450 million years. In the north is the volcanic Palomite orogeny that resulted from the collision between Polomia and northern Launea. The orogeny is uplifting an ocean plate trapped between 2 ranges, which is steadily elevating the Polomian ice domes. Beneath these ice sheets, bubbling magma melts subglacial lakes, which are larger than any freshwater surface lake on Bacera. The collision between Launea and Zaalea that created Paleobacera closed the subduction zone where the 2 continents were sutured together. However, the west coast of Zaalea continued subducting. The stress tore off crust from the opposite shore of the Paleo-Tyche Sea, creating terrains that eventually collided with the western coast of Zaalea, only for the subduction zone to reopen on the other side of the terrain, continuing the process. The current metrite orogeny is in a subduction phase of the cycle, pulling in the superterranes in the Tyche that we currently see. Finally, in the south, the Coterite orogeny began 60 million years ago, as the leading edge of Erukia accreted an island arc off the southern coast of Zaalea. Eventually, Erukia collided with the southernmost extent of the Metrades, uplifting the Thuringian Plateau and reactivating parts of the highlands. The Kotar Mountains are split into several ranges, including the Cavalisians in the west, the central Thuringians, and the eastern Kabutars. Just as these orogenies are the product of tectonic forces that stretch back deep in Dove's geologic past, other geosystems are directly influenced by the topographies that mountain building and plate movement shape. From this low-resolution map of surface elevation in kilometers from sea level, we can see the general topography of Bacera. In the north, the highest point of elevation is the East Polomian Ice Dome at 3.8 kilometers above sea level, which is slightly taller than the West Polomian Ice Dome at 3.2 kilometers. From these heights, the ice flows in every direction. The tallest ranges of the Palomar Mountains are only visible above 2 kilometers, where they pierce through the ice sheets, advancing south into Launea. The interior of Zaalea is a large platform basin of old Cratonic rock that gently rises in the east through rolling hills, old ranges, and deep valleys, until reaching the Urzetekis. These towering mountains are so tall that alpine ice fields accumulate in the tropics. To the west, uplands from old orogenies during the formation of Uya separate the Alaean coast from the inner basin. While the Metrades are not as extensive as the Urzetegis, the volcanic ridges are home to some of the tallest peaks on Becerra. The transmetrine interior is divided into hills and uplands that slope east to coastal lowlands. In the south, the Zaalean cordillera curls into the northern slopes of the Thuringian Plateau. Caught between Zaalea and Erukia, the plateau hosts the highest summits that climb over 8,000 meters above sea level, though ascending these giants would pose a challenge to even the most skilled mountaineers, since they are surrounded by fields of ice kilometers thick. Surface elevation from sea level has immediate effects on the two building blocks of climate, precipitation and surface temperature. Mountains interact with atmospheric circulation as barriers to wind or sites of high and low pressure. Temperature reliably decreases with altitude, and the difference between a humid jungle or a mild meadow in the tropics depends on elevation from sea level. First, we will take a tour of surface temperature at sea level during the height of summer. Dove has a similar orbital period and variation in axial tilt to Earth, which produces distinct seasons. During the Dovian equivalent of July, average surface temperatures across most of Becerra are quite mild. The hottest average temperatures in the northern hemisphere during the summer are found in the deserts of western Becerra, where the average daily temperature in July exceeds 30 degrees Celsius. Separating the Ulayan and Lernaean deserts are the Urzetegis, which stay below an average of 0 degrees Celsius, even in the tropics. To the north, the East Palomian ice dome is a bone-chilling negative 30 degrees Celsius on average in July. The ice has a very low albedo and reflects sunlight away from the planet. This creates a feedback loop, since colder temperatures allow the ice to grow and then cause more cooling. At sea level, the 0 degrees Celsius isotherm reaches about 48 degrees north at the foot of the Palomian ice sheet, a few hundred kilometers north from the shores of the Taiki Sea. The eastern coast of Zaalea is warmed by tropical currents, though the hottest average temperatures are found on the arid cismetrine coast of the Taiki. However, Erukia is in the southern hemisphere, and July is the middle of winter. Polar water is brought up by cold currents that cool the southern peninsula of the equatorial subcontinent below 18 degrees Celsius. Like the Urzetegis, the heights of the Metrades, Thuringian Plateau, and Kotars are above the snowline, which allows the ice fields and alpine glaciers to grow throughout the year. Taking a global view, seasonal sea ice retreats to 60 degrees latitude in the northern hemisphere and expands beyond 35 degrees latitude in the southern hemisphere. It's not unusual for currents to carry icebergs off the southern coasts of Zaalea or Erukia in July. Now we can see the changes that occur during the depths of winter. The average surface temperatures during the Dovian equivalent of January shows us how intense the seasonal changes are on Becerra. In the north, the East Palomian ice dome reaches a frigid monthly average temperature of negative 82 degrees Celsius. The 0 degrees Celsius isotherm reaches 20 degrees north on Lernaea and Zaalea at sea level, though the 0 degrees Celsius isotherm is forced north over the Taiki because the sea receives warm, tropical water from the Agathie, which helps moderate temperatures near the shore and on the islands. Tropical Zaalea is insulated by the warm jet of equatorial ocean currents, but even then, blizzards are not uncommon on the edge of the tropics. In Erukia, summer in the southern hemisphere brings equatorial currents along the east coast, warming the subcontinent and insulating the peninsula from cold currents. In tropical Zaalea and Lernaea, the temperatures are quite stable due to the consistent insulation from Dove's star and the warm waters from equatorial ocean currents. However, temperatures in the Zaalean cordillera become quite cold, with similar temperatures to the Thuringian Plateau found in the Urzetegis. During January, seasonal sea ice expands to about 40 degrees latitude in the northern hemisphere and retreats to about 60 degrees latitude in the southern hemisphere. Icebergs ripped from the northern ice pack frequently float along the coast of western Zaalea. While Becerra has mild average summer temperatures in July, the colder winters are felt well into the tropics, and this has implications for the atmospheric circulation. The second building block of Dove's climate is precipitation. Moisture is transferred from maritime air masses to the land by surface winds moving from areas of relatively high to low pressure. During July on Dove, the atmospheric surface pressure in the northern hemisphere is low over land, which means heat is rising, pulling in surface winds in a counterclockwise cyclone. We can see that a large low pressure system forms over the Alain cordillera, driven by the immensity of the Urzetekis. The North Urzine Low draws in moist air from the Aphrodite Ocean in the west, the Agathis Sea in the east, and as far south as the Astarte Ocean. Eastern Basara hosts two low pressure systems in July, the Turungian Low at the equator and the Metrine Low in the north. The Turungian Low brings most of the moisture that Erukia receives throughout the year. However, in most of the subcontinent, this occurs during the southern hemisphere's winter. In northern Laonea and Zaalea, the relative difference between the surface temperatures of the Palomian ice sheet and the adjacent soil and vegetation create a low pressure trough, which includes the Metrades Low. This cispalamine trough draws moist winds from the Aphrodite and the Tyche, which allows the ice sheets to grow throughout the warmest months of the year. To the south of the trough, the Tyche reliably develops a high pressure area in the summer. The anticyclone keeps the terrains dry, but supplies precipitation to the northern shores of the Tyche. In the southern hemisphere, the cold mass of air over the polar ice pack forms an anticyclone on the pole. A large low-pressure trough forms due to the temperature difference between the surface of the sea ice and the relatively warmer waters, which causes snowstorms across the archipelagos of the Astarte and South Aphrodite Oceans. Now, looking at January, the low-pressure area that dominates Basara in July reverses as cold air masses form in the north over land. The low-pressure system in the Alain Cordillera migrates across the equator. The South Urzine Low brings moist southwesterly winds from the Aphrodite, southeasterly winds from the Astarte, and easterly winds from the Agathi to tropical Zaalea and Laonea. Off the eastern coast of Basara, the high-pressure system over the North Aphrodite strengthens, driving winds across Zaalea and Laonea. On the opposite side of the North Urzine Peninsula, the relative temperature differences between the seasonal sea ice and the Aphrodite produces a low pressure area. The confluence of these two systems causes winter storms across northern Zaalea. High-density masses of cold air over the Palomian ice sheet descend from the heights of the ice domes, aided by gravity, to create dry katabatic winds that reach hurricane speeds. When these winds reach the shores of the Tyche, snow squalls and fog banks form over the warm water, which then roll across the sea and bring winter precipitation to the terrains and the west coast of Zaalea. In Erukia, the intercontinental convergence zone drifts south over the peninsula, following the thermal equator. Warm, moist masses of air from the Agathi, Tyche, and North Aphrodite precipitate on the northern slopes of the Kotars due to orographic lift, creating a rain shadow over the interior of the subcontinent. In the southern hemisphere, the high-pressure trough across the Aphrodite and Astarte has broken up into discrete highs by low-pressure areas that connect the trough around the south circumpolar current with the ITCZ. Combining these two building blocks, the average surface temperature and winds from January and July, we can make a low-resolution global climate map of Dove. Before we have an overview of Basara's climate, we will quickly review the Köppen-Geiger classification system that I'll be using. The monthly average temperature of tropical A climates are higher than 18 degrees Celsius throughout the year, and largely found between 15 degrees latitude north and south on Dove. Arid B climates are between 40 degrees north and 10 degrees south, and occur where evapotranspiration is higher than precipitation. Mesothermal climates are humid, with mild winters, where the coldest month's average temperature is above 0 degrees Celsius. These are usually between 10 degrees and 30 degrees latitude at sea level on Basara, though they are found in oceanic zones as far as 50 degrees latitude and near the equator at high elevations. Microthermal D climates are also humid, but with cold winters, where at least 1 month's average temperature is below 0 degrees Celsius. These occur between 20 degrees and 55 degrees latitude at sea level. Finally, the monthly average temperatures of polar E climates are below 10 degrees Celsius year-round, and are found as far south as 45 degrees north at sea level on Basara, though alpine E climates begin at elevations of around 1.7 kilometers near the equator. Equatorial western Basara has monthly average temperatures above 18 degrees Celsius, and the southern hemisphere AF climate zones receive plenty of rain all year. The humid zone extends along the shore of the Agathi. A corridor of monsoonal wet summer, dry winter climates caused by the North Rhine low separate the southern coast of Zaalea and the southeastern coast of Laonea from two great deserts. The Alaean Desert is cooler due to the proximity of cold currents and the relatively higher elevation, leading to predominantly cold, arid, and semi-arid BWK and BSK climates. The more continental Laonean Desert has extensive hot, arid, and semi-arid BWH and BSH climates. The peninsula northern Alea is covered by the North Aphrodite High in the summer and battered by low-pressure storms in the winter, leading to wet winter mesothermal climates, with warm summer CSB and cold summer CSC and microthermal DSC climates. Hot summer microthermal DFA climates fringe the northern boundary of the Great Laonean Desert, but lower summer temperatures transition through warm summer DFB and cold summer DFC to pockets of DFD and stretches of polar tundra, or ET, approaching the foot of the Polomian ice sheets. The Laonean shores of the Taiki are moist, microthermal hot, and warm summer DFA and DFB climates. The interior of eastern Laonea benefits from summer rain driven by the North Rhine low, but the microthermal DW region is created by dry continental air masses from the west and cold northerly winds during the winter. Polomia is almost entirely covered by an expanding polar ice sheet, or EF zone, where the annual average monthly temperatures are below 0 degrees Celsius. Only on the northern coast of the Palomine Peninsula is there a thin strip of ET and DWC yet to be swallowed by the ice sheet. Climates of eastern Becerra are governed by the Zaalean cordillera, which drives summer lows bringing precipitation to eastern Zaalea. The Metrady Mountains also block warm maritime air masses from reaching the eastern shores of the Taiki, leading to a CSB region that transitions to a coastal hot desert towards the equator. Likewise, the Metrades creates a rain shadow that prevents moist air from reaching Zaalea in the winter, which creates a pocket of DWA, DWB, and DWC climates in the northern interior, and AW, CWB, and CWC in the tropical interior. Despite the cordillera, much of Zaalea receives a warm, moist wind from the Aphrodite throughout the year, leading to a variety of moist tropical, meso. Up until this point, we've taken a global perspective towards the geosystems that impact Becerra and directed our attention to dynamics at work on the subcontinental scale. Going forward, Erukia will be the focus of the series, so it'll be worth acquainting ourselves with the major regions and examining the regional climates in more detail. Welcome to Erukia, the equatorial subcontinent. There are 8 regions in Erukia. Starting in the north and moving counterclockwise, there's the Thuringian Plateau, the northern coast, the western savanna, the southern rainforests, and the eastern peninsula. Now, for the interior, from east to west, there's the river valley, the Aravanian highlands, and the desert basin. Since the Thuringian Plateau is covered by ice fields and therefore uninhabited, we'll leave it out from the climate zone review. Here we have a high-resolution Köppen-Geiger climate classification map of Erukia, so we can have a more detailed look at the unique regional climates of the subcontinent. Much of the north coast is tropical at sea level and wet year-round from the Agathis Sea. In the winter, moist winds move parallel to the coast, and dry fawn winds descend from the Thuringian Plateau, creating a stretch of tropical wet summer, dry winter, or AW climate between the rainforests and the cismetrine hot desert of Zaalea. The Thuringian low during the southern hemisphere's winter brings monsoon rains to the western savanna that flood low-lying grasslands and fill seasonal lakes. During the summer, the Kabalisian range of the Khotars creates a rain shadow that dries the savanna, while a seasonal increase in glacial melt causes rivers to overflow their banks into wide floodplains. These dynamics create a tropical dry summer, wet winter, or AS climate region. Like the northern coast, the southern peninsula receives precipitation all year round, though the northern drift of the equatorial currents during the winter decreases average surface temperatures as low as 15 degrees Celsius at sea level. There is a strip of hot summer, wet all year, or CFA climate, where the tropical ocean current warms the coast, while the rest of the peninsula is characterized by warm summers and no dry season, or CFB, and some uplands of the Haxian Hills have cool summers, classifying them as CFC. Between the slopes of the Aravnian highlands and the CFB, the rainforests are AM and AF. While the southern rainforests and those of the jungles of the northern coast are relatively close, the dry expanse between them has created distinct ecosystems. The Eastern Peninsula is a mosaic of climate zones. In the southwest, the Eastern Peninsula shares the AF area with the southern rainforests, which transition to an AW climate area, where July northeasterly winds deposit their moisture on the northern slopes of the eastern Khotars. The reverse is true for the Eastern Peninsula along the Aphrodite Ocean, where southwesterly winds from the Astarte precipitate on the southern slopes to create an AS region. At the tip of the peninsula, these seasonal changes transition to an AF region. The river valley, which earns its name from the numerous tributaries flowing from the Cavalesian Mountains, Thuringian Plateau, and Aravnian Highlands through the region to the Astarte, shares the same climatic dynamics as the western savanna and is characterized by an AS climate. The Khotharite orogeny has uplifted the valley behind it, raising the average surface elevation to a few hundred meters above sea level. However, the highlands and plateau insulate the valley from the moderating effects of the ocean, leading to warmer temperatures. The Aravnian Highlands are a complex upland region that began forming after the breakup of the supercontinent that preceded Uya, that has undergone episodes of mountain building from collision, accretion and subduction, isostatic adjustment, and is the site of a large igneous province eruption. Most recently, the highlands were uplifted and reactivated by the Khotharite orogeny. The average elevation of over 500 meters transitions the AS climate at sea level to warm, dry summer, wet winter or CSB climates, with higher elevations in cool, dry summer, wet winter or CSC climates, and even alpine tundra ET climates where temperatures are 10 degrees Celsius or below year-round. Some of the valleys and basins receive little precipitation, creating pockets of cold semi-arid or BSK climates. Glaciers cap summits throughout the highlands, though the largest ice fields are in the western mountains, where the average monthly temperature is below 0 degrees Celsius throughout the year. Finally, crushed between the Cavalesians and the Aravnian highlands is the hot and arid desert basin. Like the rest of Trans-Khotharine Erukia, the basin receives trace precipitation from the north during the summer. However, the distance from the Astarte Ocean and the rain shadow from the highlands means little moisture reaches the region in the winter as well. Nevertheless, there are many important rivers fled by glacial melt, and the headwaters of the longest river on the subcontinent begins in the west of the desert basin. At lower elevations in the east, the desert has monthly average temperatures above 24 degrees Celsius all year, making it a hot arid or BWH climate, surrounded by a strip of transitional hot semi-arid or BSH climate. The higher elevations in the west lead to lower temperatures and a cool arid or BWK climate. CSB and CSC climates are found in ranges from the highlands or the Khotars, which are at such a high elevation that there is some precipitation in the winter and very little evaporation. Now we're acquainted with the climatic landscape of Erukia during the present era, on the eve of the first people migrating onto the subcontinent. This chapter provided an introduction to the physical geography of Dove, from the last supercontinent breakup 500 million years ago to the recent formation of Basera in the present era. We took a global view of the geosystems that shape the current climate of Basera and explored the equatorial subcontinent of Erukia in closer detail. In the following chapters, we'll shift our attention to the creatures that call Erukia home, beginning in the unique tropical savanna ecosystems found across the subcontinent. I hope you'll join me next time as we continue to explore lands unknown. Thank you for sharing the first video of this series and the first proper video on this channel with me. It took a little longer than I anticipated, but I decided early on that I'd like to make all the assets myself. I expect the next chapter of the series to be released in January, though I do have a supplemental video in the works outlining the process and decision making behind Dove. Perhaps I could answer some of the questions about Dove as well. If you really like what you saw in this video and want to help me continue building Dove, then you can support this project on Ko-fi. Thank you again for watching, and I'll see you next time for some soft Spec Evo.